Hello everyone. So due to some technical issues I had in class, I couldn't finish my slides, and also I couldn't share my slides in Zoom. I decided to record the entire class again, so people that joined from home, and especially people in reserve duty, can understand this material. I think many of the subjects here can be useful for your projects. Maybe you can take inspiration out of them, because what I show here is in a way fundamentals, skills that current neural networks don't solve well enough, and maybe we can extend the ideas that I will show here to new techniques in the project. So let's just begin. And again, everyone, and especially people in reserve duty, if you have any question, please feel free to reach out to email. So let's begin. So the lecture is a bit like a history lesson. So let's start from the year 2015 and see how people have evolved ideas into what we have today. So the entire field of deep learning started with the ability to embed data, specifically images, with a deep neural network. Those were usually with convolutional layers. And what people started to see is that when you are using a very deep architecture, you can see that each time if you look on VGG, you see that the spatial dimensions are reduced. So it's kind of take the spatial information and make it more compact but semantically better. And as we are getting to the final layers, they are more task specific, and specifically what people have managed to solve with deep neural network is image classification. And I think what was the main boost with this kind of network was not the ability to solve image classification, but by solving this task with a deep neural network, people could do something else, and they could achieve a very good representation of images by taking the deep layers and the deep neural network and just remove the less fully connected layers. Those are usually trained specifically for the task. So if you remove them and freeze the other layers, you can get a very good representation of the image that holds most of the useful information for classification tasks. Now, to solve classification tasks, you need to know how to recognize patterns and to have some spatial understanding of different body parts and so on. So those representations, people have found out they are extremely useful. And they could take them to different tasks by training on top of them a different fully connected layer to solve something else. So as you can see here, you freeze the entire network and just train the less fully connected layer. So this technique was the main game changer, because now we could solve many different tasks that involve images, and we couldn't do it before. One of the futuristic tasks that people could have started to look into was visual question answering. So now if you have an image and a question, we could have a technique that will be able to understand the language. There was some initial works on how to do similar things in NLP. It wasn't as good back then. Now NLP have become much more dominant, but at least now we could represent the image very well. So it means that we can get a representation of a sheep, of a child, of a plastic container with a vector and semantic representation. And this is something we didn't have before. And what can we do with this representation? So one of the earliest work that solved this task just took, as you can see on top, a CNN, This is a deep convolutional network pre-trained, and took the representation and added it to the decoding process of LSTM. So what you can see here is a sequence-to-sequence network. It uses an LSTM to encode the question, what is behind the table, and it adds to each step, to the hidden step, to the hidden representation, a representation of the image. So when it generates the answer, when it decodes it, it is aware of the image. So you could realize that during training, it learned to take it into account to generate the right response. So it's very naive, but it's also one of the first time we actually could solve this task. And it's something without deep neural network we couldn't do. Now, the next way to improve on a task that involved image was to use attention. And what was the main issue with the previous attempt? So in the previous attempt, we just took the entire image. Now, if you think about how LSTM works, each time it generates a word. And I think intuitively, you'd say each word should refer maybe to different place in the image. Now, in image captioning, it means that when you are describing the image, you don't want it just to have the entire information of the image class, because then all you will have is this is an image of a bird. You also want to maybe describe the background, that it's fly on over a body of water. And to do that, people have thought, okay, I need to have a representation of different places each time I generate a token. So the way to do it was with another layer, another module, attention, that during the decoding could look at different places, or in a way could learn to give more weights to areas in the image that the LSTM will take into account. So it will allow it to describe the bird, and afterward, when it looks on the background, it will describe the water. And how they do that? So, okay, so first of all, this is what we already discussed. Every word they describe different places in the image. And the way they do it is with soft attention. This is how it was called. So the idea is that you can take from the deep neural network a representation that includes spatial dimension. This is the dimensions of the image. So you can see here there is some form of a grid, and the attention unit, what it did was learning how to weight those different areas in the image to allow a weighted sum that will the end result will be just a single vector that only takes information from some parts of the image. So in the bottom, you can see how attention works. Basically, the main idea of attention is to learn the attention weights for AI. AI is different locations in the image. Each area AI is represented by a vector, and you can get the A representation, the one you see on the left, from the deep neural network by taking a representation before the fully connected layers. The fully connected layers usually took the entire image and just dropped it with some form of a pooling or something else to a single vector. You need a representation that includes the spatial location to apply attention. Also important, the attention weights are learnable. This is the main concept, and you learn it end to end. Like you learn it when you are training for image captioning. So it knows how to learn that different areas are good for describing an image by in the training process. Now, how do you learn the attention weights? So usually there is an attention function. Like here in this paper, they took the location AI and the previous hidden state of the LSTM to learn ETI. This is usually the attention belief. It basically just tells you how important is each region, and then you are applying on those all beliefs, all those weights of different areas in the image. You take a softmax on them to get a probability, and this is the weighting for each area in the image. And where else it was very important in VQA. So in visual question answering, you can see that when we are asking what animal is in the cage, we want the model to ignore all the parts of the image that are not relevant to the image and just focus on the animal. And we can also see that it's highly dependent on the question. Like if we are now asking what color is the plastic container, we want the attention to look on the plastic container. And why it's slightly different than what we saw in captioning, mainly because of that. Because now we need to take into account the question to make attention over the image. So beforehand, we took each area and used it to create the attention weights. Now we'll need to come up with a way to know how important an area in the image. You'll need to take into account the question. So it needs to be different because you need to take into account information from the question. So the paper that solved that was Ask, Attend, and Answer. It was built on top of the ideas of the previous method for image captioning. You can see even the similar title, and it was released just a year after the captioning technique. And you can see here that they showed you that when there is a question, what is the child standing on? So they even showed that the attention kind of learned that where is the child, and they even showed that every word reinforces some different area or correlates with different areas, and this kind of start to give you the intuition how they built the attention unit. So what they actually want is to have a way to learn correlation between words and areas in the image, and then they can understand which areas are important by learning the areas that correlates more with the question. So the module that they have designed called word guided attention, it learned a correlation matrix. So in a way, what it tries to do is learning by weighted dot product how much each word correlates with different areas in the image, and then they took a max on top of it. So it means, let's say you are asking how important a region in the image is. You are creating correlation with all the words, and then take the max of all those correlations to be the potential, to be what I showed you before, the attention belief. So now they have potential, they apply softmax, and you get a weighting for the entire image based on the question. So this was the first attempt, which is quite similar to what we even have today, to have a word-guided attention, or given another modality, how we can attend based on it to a different modality. So one modality is the image, the other is the question, and now we have a technique to attend to the image based on the words by building this correlation matrix. Another technique that they showed is that you can even apply the attention again, maybe resemble a bit how transformer works. We'll talk about it later. So what they said is that you can create attention over the, let's say, the image. You get one vector that represents the image. You can now add it to every embedding of every word in the question. So the question is now aware of the image, and then you can calculate correlation again and return the entire process to create another attention map. So intuitively, you attend one time, you get attended vector, you can add it to the question and repeat the process. You can do it how many times you want, and you'll get attention that maybe is based on the previous attention. So maybe it starts to resemble a way of chain of thoughts, that like you are solving a problem with more than one step, and they even showed it visually with some qualitative results. I'll be honest, it's probably cherry-picked, but what you can see here is that given the question, what is the color of the object near the bed, they did show that the first time they applied attention, it first found the bed, like the item that you need to relate to. And then when they applied attention again, they found that the object is pink, because they knew based on the previous attention where they should look for items that are near the bed. Honestly, as I said, it's probably cherry-picked, but what you can see here is the issues that you have with question on images. One of them is relational thinking, like when you are trying to answer based on relation to other objects in the image, it becomes more complicated. And even back then, people started to come up with ideas how to solve it. Even if they couldn't really solve it, at least they could say they are they have the first attempt to solve it, which is also important, because now everyone will want to solve this issue. Maybe it will need to cite them or to relate to them, and this is a bit how academia works. You want to be the first one that comes up with a solution to a very important problem, and relational thinking in image question answering is extremely important issue. We have challenges to solve it even today. So this was attention for question answering, and the same year another lab came up with an idea about how to make co-attention. Co-attention means that instead of just attending to the image, you can even attend to the question. You can attend to which words are important to answer the question. And here they showed two techniques. One of them, again, calculate with the correlation metrics in parallel, both for the question and the image. You can realize that if you take the max to get how much an area in the image correlates with the question, you can take the max over the rows, and you can take it over the columns. And if you do that, you kind of get also what are the important words based on the image, something along those lines. I'll let you, if you want, look into the paper. The formula there is not very intuitive, and I will show you later on works that we have done that make it much more intuitive. Another attempt was, okay, we want to attend both to the question and the image. How can we do it? So what they did was, suppose we start with attention over the question, we can then do attention, we can then add the attended vector to the image, attend to the image, then add this representation to the question, and attend to the question again. So this was alternating co-attention, where you just do it like a coordinate descent kind of thing. Like you start with one modality, you optimize there, then you take this result, add to the other, optimize on the image, and by doing this manipulation, you can get attention on those two modalities. But to be honest, it's very hard to use this technique if you add more modalities. Let's say you have 3 modalities. It's not trivial how you do this alternating co-attention technique. And so the co-attention results were quite nice, because now we even have attention over the questions. And for instance, if the question, let's say on the second row, is what is the color of the bird, it could attend to the word color. So it means that to answer the question, all you need to know is just the word color. So now the model can get you the color without all the extra words. Once you attended to the bird, it's no longer needed in the question. So this is why it was quite useful. You see here 3 types of attention. You can get into the paper to understand why. They've made something about hierarchical attention. I'm not going to get into those details, but also because looking back retrospectively, it wasn't that important. What was more important is the idea of creating attention for 2 modalities at once. Now, what's good in attention? Attention also provided explainability. We could easily understand why a model answered in a way. So here we have a few questions. If the question is about the bus, you can see the attention looks on the bus. If it's about bikes on the street or sidewalk, you can see it looks on the street. And when the question is what is the weather like, it looks on the sky. I even added the actual answers just to show you that on the last question, when we ask what is the weather like, the model answered cloudy, and the ground truth was it looks sunny and warm. Now, if you try to analyze why it made a mistake, you can look on the attention to understand it looked on a cloud. Now, it's a bit hard to see here, but you can see that what it actually attended to is a cloud, and you can realize why I made this mistake and even understand that it wasn't a mistake. And also, I mean, it's on the same idea. You can even compare different models. Here we have 2 techniques that in one of them the answer of what color are their coats was red, and you can see it's because it looked on the red light in the background. It helps a lot in explaining how the model works, and we'll talk about it a bit more later. Now, what I want you to think about is how to. So, in a way, it's what we have focused in my PhD research, is how to create a general multimodal attention. And what it means to have a general multimodal attention, it means that it doesn't matter how many modalities you input the network. Now, what we have seen is image and a question, but let's say even if you just take a video, there is another modality, which is the sound. If you think about modalities as a part of the input, you can even take a video and break it down to different frames, and each frame could be seen as a modality. Now you have many images, or if let's say you have a dialogue over something. Dialogue means you have a history. It means you need to attend to each sentence in the history differently. So what you would want to have is a way to generate a belief, attention belief for each modality in a way that it doesn't matter how many modalities you have, the technique remains similar. And the previous technique, they were very ad hoc solutions for 2 modalities. So if you needed to have more, it wasn't very intuitive how to do it. So let's recall again the attention equation, and it has 2 parts. So one of the parts is a representation of a region in the image. Here it's a grid, it could be anything else, but what you want to have is to have a weighting for each area to tell how important it is. So here we have a representation of, let's say, in the middle of this area, and we have a vector for it. Now, the attention belief, what we are trying to find is a weight, how much this area is important. Now, here we have BI. Why we have the capital I here is because it's the belief for the image. We want to build how much each area in the image is important, and this belief should take into account any parts of the input. What it means, it shouldn't just take into account the representation of this area. It should take into account other areas in the image, because the context give you information how important this area is, and it also need to take into account every other modality that you have in the input. But just to start simple, let's say we only have a question. So Here, it's the main point of our method. We try to come up with a general way to break down the attention potential from any kind of input. What it means that if we want to know for II, it's a location in the image. If we want to know how important this area is, we need to get information from the local, the vector that represent this area, and global from all the other modalities. If we just have the question, we have here a message from the question to the image. Now, the message should take into account interactions with the other modality here is the word, and the local should take mostly information from the area that we are looking at. And also we added trainable scalars to calibrate if you want to rely more on information from other modalities or on information from just the local area of the image that we are now trying to weight. So with all those elements, we created a single weight that tells us how important this area. Also note that the notation here with the exponent and the prop 2, the proportional 2, it's just a way to write a softmax. So we apply a softmax over the score in the middle. So now we'll try to define it more as a graph. So as I said, we have different modalities, and each modality we can look at it as a node. And when we are trying to find out the belief, how much each word is important or how much each region is important, we'll take into account two factors. As I said, one of them is the local. So you can see it's in a way just a vertex to itself. And the way we define this local information is just with a two-layer multi-layer perceptron that takes the representation of this area and drop it to a single score. Maybe there are more complicated ways to do it, but we try to keep it intuitive, and this is, I think, the most intuitive way to do to take a vector of a region and drop it to a single score, how much this area is important. Now, note the capital VI here are weights, and they are trainable, and the way we learn how much each region is important is end-to-end. Like those weights are trained based on the task of question answering. If we'll take this architecture and train it to solve something else, the weight will be different. So it learns how much each area is important. Now, what we can see is maybe it can reveal biases in your training data when you just consider the local information, because what it tells you is we learn how much an area is important only based on this area. So let's say here we have two different questions. You can figure out it's going to be the exact same attention for the two images because it doesn't take into account the question. And we can see it emphasized like the shirt of the women here and the plastic container and the animal face, but it does ignore some parts of the background. Maybe they are important, but the local information at least told us that given the entire training dataset, these are the important areas only based on the image information. So if we want to ask something about the background, maybe it can be problematic in this type with this training data. So maybe it will tell us, okay, maybe you need to ask more questions about the hay in the background and so on. And now we can talk about the interaction factor, the one that I told you need to account information from another modality. So for that, we'll need to first define how interaction can be done. And the most intuitive way is just dot product each area in the image can be represented as a vector. We already know that from deep neural network. And each word can be represented as a vector as well. We know that we can use LSTM and so on to represent words. And a dot product between those two will give us a score that tells us how much they correlate. Here the correlation is very high because the animal, the word animal and the face of the sheep, they represent similar concepts, and it can learn that those areas correlate. Now, how we build this interaction score then? So first of all, we do embed the representation of the question and the representation of the image to again. So in a way, it will form a multimodal embedding, a place where they can interact. So the model learned that. So you can see here the capital L, Q, and the RI. The terms here is like left and right because it's very general. It embed again, and afterwards we create the dot product. We multiply those two representations, and we also normalize before, and we need many normalization because when two modalities interact, we need to always keep in mind we need to normalize things for it to actually work because they come from very different distribution. So we embed again and normalize and then create the dot product. And what we have as a result, what we get is a correlation matrix, just like before, that tells you how much each word interact with different parts of the image and vice versa. So here what animal is in the cage. This is how the correlation matrix could look like. Obviously there are many other parts of the image, so it's much bigger, but this is just a small representation of how it could look. Now to create the potentials, for the messages for the potentials, we do marginalization, which is basically just a weighted sum. It could be a max operation just like we saw in the previous paper, but we found out that sum over the matrix is better, and even the summation is something we do weighted. So here, after the summation, what we are left with is our potentials for each area in the image, and we can do the exact same thing to get how much each word is important given the image. So we have a message from the question to the image and from the image to the question. And now those messages, this is the weighting they give, and you can see it's much closer to what we expect the attention to be given a question. So now when the question, what animal is in the cage, you can see that it emphasized the sheep face. And when the question is what color is the plastic container inside the cage, it emphasized the plastic container. So summary up until now. So now we have a way to create attention for two different modalities by learning the local potentials for each one of them. And again, it's not a separate part. Everything is end-to-end learning from the task of answering question. It's just more weights in the architecture. And so we learn the local potential for each one of the modality, and we learn how to send messages between the different modalities. And by that, we are getting BI capital I, B capital Q. Those are the belief how much each word is important and how much each region in the image is important. So we can take those weights and have a weighted sum over the representation of the question in the image and get a single vector. And with a single vector, after we apply attention, it's very easy to have a fully connected on top of it and solve any task. So in a way, we have here a way to do pooling, like reduce all the spatial information of question or image to a single vector in a way that takes into account the other modalities. It's extremely powerful and can be used to any, even nowadays, architecture that have pooling or something like that tries to take spatial information and reduce it. Now we have a way to condition on the other elements in the input to do that in a much smarter way. This is some visualization, just again to give you intuition how it works. We that just visualize what the network they've trained, what we see again is that the local function learns just important areas in the image to solve the task of visual question answering. The messages from other modalities give you what areas are important given another modality. So here it's this is the message from the question to the image or from the image to the question. And the final belief is adding those two together with calibrated scalars and apply softmax on top of it to get a probability. And you can see it actually get us the very nice result that we started with. And this approach created a very strong VQI baseline. We showed it in a paper in 2017. You can see that the architecture itself has those two elements of local and pairwise. Now, I will say that in this paper, we even extended this concept to correlation with three modalities by introducing a ternary potential. So in ternary potential, we have a correlation between three modalities. You can think about it that how much a region is important based on an image and based on another modality. Here, the other modality was a multiple choice. So when you answer a question, there was a setup that they gave you some possible candidates to pick up from. And we also needed to attend to those because an area is important only if the possible answers are related to this area. So we needed to take another modality, and with ternary potential, we took higher order correlation. So this was another novelty that we showed. And then the network became a bit more complicated when you add more modality, because now you have many more pairwise potentials between different modalities, but also we have the ternary potential that takes all of them into account. So this was the main idea of the paper we released in 2017. And over the years, we extended this idea to be a general graph that can take any number of modality by defining the pairwise interaction between them, between those two modalities. So the graph that you saw before is actually correspond to the task of visual dialogue. In visual dialogue, you have 10 questions and 10 answers in the history. It's a fixed number. If you have less, we just pad it. And we need to have attention for each question separately. And you can realize that if you have 10 of those, it's going to be 20 attention maps overall, one for each question and one for each answer. And it's very difficult to think about how you infer attention for each modality separately. But with our approach, it was very easy to extend to any number, because we just need to factorize the information from all the other modalities into pairwise potentials. That means that if we want to know how much attention we have for an area in the image, we need to take into account all the input. But now the way we do it is by creating interaction between the first question and the image, the first answer and the image, the second question with the image, and so on. So we create many potentials, but we actually broke down a very complicated input into pairwise factors. So it's not that complicated. And the way we formalize it is just like before. We have messages. So you see here for the image, we collect messages from many different modalities, and we just need to take all those messages and sum them. So utilities are the different modalities, and we sum all the messages to get one belief. So it extends the same concept that we had with the question to any number of modalities. And what it allowed us is to create attention for many modalities all at once. So now when we have a dialogue, we have many history interactions. We also have a caption that they added, answer options. This is again a multiple choice setup. And you can see that from the input that have spatial information about each one of those modalities, after factor graph attention was applied, we end up with a single vector for each modality. Now this representation is very concise and it's easy to take it. What we did here is just take this representation, concatenate it to each possible answer, and then have a weighting, a fully connected weighting for this option. So again, we have a very useful way to take a big input with information, with spatial information, and just have attention layer to remove all the unnecessary part based on the interaction between those modalities. There were some other techniques, like some interactions are very similar, so you don't need to learn how to embed before you apply the dot product. You don't need to learn for each type of interaction between modalities. You don't need to learn a separate weights. Maybe you can use the same weights. If anyone wants to think about it, there are many ways to improve the way we represent this graph by maybe removing some interactions, and I think there are a lot of potential here to make it more efficient. So if you have time, look into the paper and you'll see some insights that we have. There is a big room for improvement. And in general, we had many papers taking this concept of a graph attention, a way to create attention for many modalities, and we applied it to tasks that honestly are very complicated and usually are solved very naively. And just by adding a smart attention, we could solve them. So I already discussed about question answering and dialogue, but we also solved the video dialogue when you have a video and a dialogue, or video retrieval, or visual storytelling. It's a task where you get 5 images and you need to create a story that describe them. Again, we created it with factor graph attention. There was some special tweaks just for the task, but the main building block is to create attention for each modality in a way the other modalities can interact with it. Hey, so I took a little break. If you need one, this is a good time to take it, because we are getting into new area, new subjects. So what else happened around the years that all the progress in multimodal attention models came? There was a revolution in encoding. Now, encoding is the basic, elementary, fundamental block of any deep learning architecture, and this is the reason why encoding, changing something in the way we encode some representations, it's going to make a big impact on any architecture. So encoding, what is it? Is the way in the network to transform from representation V. It has spatial dimension like words or areas in the image. You already know that, and each area, word, and so on is embedded in a vector space of with a dimension, let's say D. And in any architecture, deep learning architecture, you'll see that we take the representation and transform it to another representation and learn how to transform it. And the new representation could be in the same embedding dimension like I showed here. It could be the same spatial dimension, but it could also be reduced. And it depends on how you are making this transformation. And the question is how you transfer from one layer to another. Now, keep in mind that the way deep learning works is it takes image that has a lot of information in it and transform it to a more concise representation that is actually make the solution of the task much easier. So in image classification, it could take the image, and the final layers had they mostly consist information that is relevant for the task of classification. Because classification is so general, it means that the representation will be useful for different tasks. But the the ability to take the information, the general information, and make it concise is what made deep learning famous. And how to do those transformation is the most important thing. So after I gave enough motivation why changing encoding is important, let's see some ways people do it. So the most naive way is just take the entire representation and linearly transform it to a different representation. You can keep the same dimension with enough weights, and that in a way means that every number in the new representation is connected to all the numbers in the previous representation. So it looks something like this, and the issue is that it will result overfitting very easily, spurious correlation, because every number connected to all the other numbers, it's very easy to pick on some false correlation, spurious correlation, something that appeared in the training, some correlation that appeared in the training, but it's meaningless, and the only reason it picked it up is maybe because there is not enough data. And I do want to mention that maybe with enough data, this kind of approach will be good, because then it will be very hard for spurious correlation to appear in many training, in enough training samples for the model to pick. And the only reason I mention it is because nowadays we have so much data that we train on, and maybe fully connected network will be back to fashion because of it. So it's a very strong network. It's not weak, but it's too strong in a way. So to regularize this, we have convolutional layers that run a kernel over the spatial dimension of the previous representation. The kernel is fixed size, and what it allows us is to take information only from the areas that are spatially close to us. So it means words next to us, or areas in the image that around the area of the vector that you are trying to represent. And keep in mind that this kernel is the same weights are applied over different areas, so it can learn general patterns. And I emphasize that the number of weights here it's much smaller, because we are no longer dependent on n. And the intuition I need you to have is just that if you have less weights, there is less chance that you'll pick a spurious correlation. It will probably generalize better. So this is also another way to see that. And in CNN, as I said, it's running filter that every time just take the local environment. So you can see it will not look on all the information of the previous layer, and this caused some issues. So the context now only limited to the kernel size, and we do have computational burden because we need to run this filter over the entire image or sentence, and it takes time because you can't do everything all at once. Though in modern GPU there are many ways to optimize this computation. Another way to encode things were with LSTM. So LSTM keeps an hidden state, that the hidden state gets information from the previous hidden state and the current word or area in the image. That way it doesn't need a lot of weights, but we still have limited context because we only rely on the hidden state, and sometime maybe you'll need something from the beginning of the sentence, if it wasn't encoded in the hidden state, it's gone. And we have computational burden again because we need to run it in over n items, and every element depends on the computation that came before, so it takes more time to encode in this manner. But again, the weights are very small, so it's less likely to cause overfitting. But as I said, limited context, and we have a computational burden. Now, what we actually want when we encode is to know which elements of the previous representation are related to the representation after the transformation. So let's say ZI is a word in the middle of the sentence. You want to know from the words in the previous encoding layer, the previous representation, which ones are more relevant or we should take into account when we make this transformation. In a way, in convolutional layers, we had this prior, we assumed it's the neighbors around you. In LSTM, we had a hidden state that should have taken into account what is more important and what's not when we encoded the hidden state, but it was very tough for him to, because this decision depends on the actual area that you are trying to represent. So what can we do to solve it? We can use attention. We can weight the previous layer. We can learn how to weight the previous layer. So when we are generating ZI, we'll know exactly how much each element of the previous representation should be taken into account when we are creating the new representation. So this is exactly what attention all you need did. It learned an attention between an element to its neighbors. This is why it's called self-attention, because you learn the connection internally, like from a word to different words. And the way to learn how much each word is related to the other, we need to build again a correlation matrix. So we embed ourselves twice. One they called it Q query. The other times it's K. We embed it twice. And after we embed the representation 2 times, we can multiply it and we get a correlation matrix that tells us how much each word correlates to all the other words. And with that correlation matrix, we apply a softmax and we multiply it with the representation embedded again with V. This is called V. So finally, after you can check by doing the calculation yourself, you'll end up with Z, and Z is a new representation with the same dimension, but what actually happens here is that every vector in the original V is going to be added up according to the attention to a new vector, and we will get a representation that can take into account the context, but it learned how to take the context. And just to visualize it, to make it more easier to understand. So again, this is something that correlation matrix could look like. Keep in mind that there is the words with itself don't have correlation of 1. It's because we embed ourselves twice, one with Q and K. So it's not necessarily going to have a high correlation with itself. And we take the correlation matrix and we use it to define connection to different vectors in the representation. So what we get is something like this, like to represent end, we can add up the word plant, or to represent began, we need to take into account the word plant and entered. So every word in the representation knows which other, what is the context it needs to take into account. And the same thing can be applied to vision, where every element in the image can be connected to any other element in the image. And what people have realized is that that is basically all we need, all we try to achieve when we encode something. This is what we try to do with LSTM. They try to tell you what is the context of every word, but it was limited, as you can see here. And now with attention, each word can be connected to all the other words in the sentence, and this is why it significantly improved the performance in many domains of NLP. And I think the reason it improved performance is not only because it was a better encoding, and those are some examples for multimodal kind of networks that used attention, that use transformer, and those were the state of the art in many fields, including VQA, and also people have trained on, as I said, massive data sets like conceptual captions that have beyond 3 million images, and resources at the university were quite limited, and we needed to find other domains to focus our research on without the need to actually develop a new architecture from scratch. Now, to start exploring what areas might need our help, we need to understand first what currently network solving very well. And one thing networks solve very well are detection questions because of the attention. So if we have questions like, can you see cars? We'll see the attention looks on the cars, and it will be very easy for the model to solve it. And are there buildings? We'll see the attention look at the building. Or are there trees? We'll see the attention look at the trees. And with that, as I said, we solved many different tasks that involve large-scale input data. And once again, the question is, attention is all we need. And the answer, so to find other issues than in machine learning that is not around attention, one way to do it is to consider what skills humans have and machine learning don't. Now, let's say we have a perfect attention, even as human, it's not enough for us to solve any question. And when you look on cognitive science, you'll see that other cognitive skills that humans have, they define those into two categories. One is perception and one is comprehension. And I just want to use this as motivation for us to find issues that we can still solve and improve on that are not around building an attention mechanism. So let's be more specific. Perception is defined as identification of input information. That means that if there is a question, we want to know what is all the relevant information. And in a way, actually, mechanisms like attention can lead to overlooking some parts of the input because we can maybe attend to something, some bias, and ignore relevant information. So, as I said, it's related to biases. And what is a bias in the dataset? So, for instance, one bias could be that for how many questions, we typically answer them with 2. What it means, every time there is how many flags are there, how many levels are on the bus, usually the answer is going to be 2. And what will happen as a result is that the model might say, okay, instead of looking at the image when we are trying to answer how many animals are pictured, will only look at the question because it is enough to answer two. Now, obviously, it can't generalize. So if there are images with the answer 4 or 6, it will just answer 2 because it doesn't even take into account the image. So one of the work we did to start even working on this problem is to quantify how much the classifier relies on a modality. So it will tell us if the model does not perceive one of the modalities. How we test that? What we can do is we can ask the same question again, but change the images and see if we change the answer. If the model did not change the answer, it simply means that it ignores the image, and we can do the same thing for the question. And just measuring an issue and show the results could be very significant, enough to publish the work. And formally, we looked on the accuracy. So we looked on the accuracy of a sample, and we tried to measure how much the accuracy changed when we permuted the image, when we changed the image across a batch, so we can average it. And if there is a difference, a big difference, it means that the model perceives the image, but if there is no difference, it means that it doesn't perceive the image. And what we found out is that state-of-the-art architecture that was released back then, actually the accuracy was better, but it was for the wrong reasons. As you can see, the perceptual score of the question was very high. It means it highly relied on the question, but for the image, it in many questions is actually ignored it. So it means that the reason it improved was because of the ability to pick biases in the question and not relying on the image, which is not how we want to solve the VQA task. And another work that we have released is about regularization during the training that we can add that helps the model keep information about the image. If you want to look into this area, you can see this paper and feel free to ask questions. But there is still a question, is this enough? So what we did in those two works was more about the ability to perceive all the modalities, that we won't ignore a modality as a whole. Let's consider another question, like who is this person? I'm sure you can answer that, but the model only relies on the data, on the training data. In the training data, you can see we have the answer Obama and the answer Trump, so it will look on the image to make the decision. It's not like all the answers are Trump, so we will ignore it. But there is another issue. So there is still spurious correlations because every time the question was, the answer was Trump, in the background there was the flag of the United States, where in the picture of Obama it wasn't the case. And this is something that happens all the time when we collect data. Sometimes it's not as trivial as here, and it's very hard for humans to pick it up, to detect that. And what will happen? So especially with attention models, when there is a spurious correlation, who is this person, what will probably happen with attention, because the American flag was very important to answer Trump in the training set. It will learn to pick on this information, and it will attend to the American flag. And after the attention, this will be the representation, something about the American flag and the word person. And from here you can tell that the model will actually answer Trump. Now, it could be actually really nice if instead of trying to build a data set without any spurious correlation, maybe we can simply teach the model where it should look. So if there is a question about who is this person, and we know that the answer is should require the model to look on Obama's face and not on the background, we can tell the model to look on the face, and then he can appropriately answer Obama. Now, the main question is how to teach the model where to look. This is a technique that we needed to develop, and I'll show you how. So, first of all, where to look annotation is something that is very hard to acquire. It's a notation that we can't find for visual question answering, but we do have it for another task, which is image classification. Because in image classification, we expect the model to look on the foreground, on the object, and not the background. And we do have a human annotated dataset called ImageNet-S that tells us exactly where the foreground is, where the object is, and exactly where the background is. So another question we need to ask ourselves about is it okay to use this task? We need to know that there is those kind of issues in image classification, and we do have them. So we do have spurious correlations. We have something we refer to as background bias, where the model looks on the background to determine the class. Here, it classified the image as trem instead of tank, because it looked on the electricity cord on the in the background. Or another issue that happens a lot is partial perception. So instead of perceiving the entire object, it looks on part of it. Here it classified the image as a ping pong ball instead of a teddy bear, because it only looked on his leg. Okay, so to make the technique, we also need to know where the model looks. So what does it mean to look at something? So for that, we refer to literature in the field of relevance map. Relevance map tells you for each class or decision the model makes, what are the parts of the input the model used or influenced this decision. And the method we use, we have a link, we have a citation here to a paper. It's by Hila, that uses both attention maps. As we've seen before, attention provides great explainability to where the what parts of the input the model is using. What is missing with attention map is a class-specific signal. So if we classify an image, the model can tell us 30% it's a dog, 20% it's a cat, and all the other classes for the image that you see. Now with attention, you'll get only attention will not be dependent on the class, so you'll probably get something that looks on both the cat and the dog, all the important elements in the image. With the gradient, you can tell which parts of the input actually influence this class, and then you can get a different relevance map for a dog and a cat. But for more information about how to generate relevance map, go to the paper. And now that we have both the relevancy map and the segmentation map, we can very easily optimize the relevance map. The relevance map is something you can actually change, and what we require is two things. First of all, we want the foreground to be high where the segmentation says the foreground exists. We want the relevance map to be high. So this is the first term. And when the relevance map says about an area it's a background, we want the relevance map to be low, so we require it to be close to 0. So this is the second term. And when we combine those two terms, we get a loss that when we optimize it, it will change the relevance map to look more on the foreground and less on the background. There are also hyperparameters here that tells you to tell the optimization which loss is more critical to solve, to improve. And what we found is that the hyperparameter that emphasize the fact that the model shouldn't look on the background was more important. So the scale of the background hyperparameter was larger than the foreground hyperparameter. Now, one thing you need to keep in mind is that every time we optimize a model to solve a new task, we also want to keep the downstream task performance high. So it means that when we change the relevance map, we also want to keep the classification abilities high, so it won't ruin the original downstream task that the model was trained for. And to do that, we have a nice trick here that tells the model to keep the same prediction as it did before. We can see it's a cross entropy with the prediction of the model, and we ask the prediction of the model to be close to argmax of the prediction. So it means to be close to the class that was actually predicted, or the maximum class that it chose. What it gives the model a way to be very sure about the class that the original classification task chose. And what we get overall is two terms. One is about optimizing the relevance map, and another one is about keeping the performance of classification good enough. And this optimization is done as a short fine-tuning, 15 epoch. It doesn't take too long, and it is using a pre-trained model that was trained on ImageNet and just optimize its relevance map. So I'll show you some results. So first of all, the issue that we saw before about the background bias. So now instead of looking at the electricity code, it actually picks tank as the prediction, and it looks on the tank. And now the prediction, instead of ping pong ball, changed to teddy, and you can see it looks exactly on the teddy. Even if we saw examples that the prediction remained the same, let's say here we can see snowplow. Now we can see by displaying the relevance map that the reason is because the model looked on the snowplow and not because it looked on the snow in the background. And what I think is interesting is when we are considering incorrect predictions, where the model have changed from the right class to a class that was not the ground truth, it actually reveals issues in the dataset. For instance, here we can see that the classification changed from a tripod to strawberry. And the reason for it is because now the model kind of attends to the strawberry, but the reason is because there are multiple objects in the image, and it's not a good image for the task of image classification, but it still appears in ImageNet. Or even some classes, I can tell that they are always appear in the background, like pool table. You can see that there are many other objects, and it's just something in the background of a party. So the model have changed from a pool table, the class, to hat. But again, the reason is because this class is not great for the task of image classification. Now, other benefits is that the method is very efficient. We only use 3 samples per class, and we didn't even train on all the classes of ImageNet. We just took 500 classes, which gave us overall 1,500 samples. It's in terms of supervision, it's not so large. I could even say it's significantly small. It's something every one can do in a week or so, do it by hand, and the fact that it can use just this amount of supervision is very important for domains like medical, that it's very hard to get public data and ask doctors to annotate information. So it was very important for us to show that you don't need a lot of information. And we even saw that it worked with Dino, an unsupervised segmentation method. So it means that you don't even need to take supervised data to improve the perception of where the model looks. Another thing that is important is that the method is robust to a different distribution of images. It improves on many different datasets that it didn't even train on, and it just shows you that when you are optimizing a skill or something that makes sense in a way and doesn't tell the model you should learn by classify, or with the ground truth you should also learn where to look, it makes the learning much more robust, because now we taught him something true about the world. You should look on the object and not the background, instead of letting him learn it as a side effect of image classification. And the only areas where we actually ruined a bit the prediction are ImageNet classes that we haven't trained on. And I think it's mostly because issues that I showed you before, where some classes have multiple objects in their images, and this is a bias that we kind of ruined. But it's okay to ruin performance a little bit on the data that you train on, if you achieve as a result a big improvements on dataset with shifted distribution. And what do I mean by dataset with shifted distribution? So the images that exist there, usually they take something that is very different from a natural image that appear in ImageNet. So let's say we have an orange on a carpet, so the context is not very relevant. So any model that was trained on ImageNet will fail significantly. As you can see here, it says it's a maze, and with our approach it actually knew that it should focus on the objects and not rely on the background, and then it could classify it as orange, and there are many other examples, even synthetic ones. Another benefit is that the method is stable. So the method had some hyperparameters in it, like to calibrate the different losses, and we could improve on many different type of transformer models for image classification using those the same hyperparameters. And again, it's important. It means that anyone uses this approach don't need significantly amount of fine-tuning to find the perfect hyperparameters. We just show that any model with fine-tuning with our method can make improvements without the need to search for new hyperparameters. So now the main question is it enough? So let's say we do have a model that perceives the input well. How can it answer a question like, what is this person known for? How can he tell that he is the president of the United States? And for that, I want us to look at a new skill, another skill that is independent of all the other, which I call comprehension. And it's defined as a higher cognitive process that involves understanding of the meaning of a concept. And what do I mean by understanding? That means that the method will know to recognize a concept. So we will know that all those images represent Obama. He will know that this is a subset of presidents, and he can even tell attributes like that a president is a president of a country. And this kind of knowledge is, to get it, we do need a large-scale training data, much larger than most data sets that existed up until now. Let's just think about how much data a human have. Now, Jan LeCun mentioned that a 5 years old that have 10 frames per second sees something like around 788 million samples till they get to the age of 5. Now, if you remember, conceptual captions and all the large-scale data set up until now were around 3 million. So we need a way to have a much larger data set to be able to have the level of comprehension needed to answer any question. So how did we achieve this knowledge? We achieved it by crawling the web. And the paper that did it was a CLIP. It was the most significant paper that appeared, that have changed the multimodal world. What it did was quite simple. The architecture itself wasn't very complicated. It encoded the text and the image both with transformers. And it learned discriminatively via contrastive loss to bring together text and images that appeared on the same web pages and to push apart text that appeared in different documents from the image. In this way, they cluster together text and images that represent the same thing. And if you can see on the right, this is what was the result. Something about the clip embedding space was something about all the countries could be in one cluster, cities in a different cluster, presidents in a different cluster, and it's multimodal. There is both text and images, and there is also relations between them. If you can see, like, the directions can tell you like how that Obama relates to maybe the flag of the American country, the same way Angela Merkel relates to the German flag. So it built a knowledge through embedding space, and this is exactly how machine learning and deep learning models can have the ability to comprehend the environment and the entities that appear in the world. Now, the main question is, how can we use this knowledge in different tasks? And it's not that easy because, again, we only learned discriminatively. It means that we know, given an image and a text, to tell if they are very close or they are very different. But if we try to solve something like image captioning, that given an image, we want to generate a caption, how exactly can we use clip knowledge to describe it as Cairo's ancient city center? And it's many wonders, like how can we get this kind of caption using clip? It's still not clear. What we do have generative language models that can generate text. Here, GPT-2, a very early version of ChatGPT, it was trained on 8 million web pages, not very big, but still very significant. And it knows very good how to generate text. And the way it generates text, it gets a prompt context, and it generates the next word given this context. And what people have come up with to use clip to generate captions is to use a mapping network. The mapping network takes the representation of clip and map it to a prefix, and then they ask GPT, given this prefix, continue the sentence, generate the caption. Now they train the mapping with a supervised phase, the fine-tuning phase that use captioning. So they train the mapping so the generated text of GPT will be a caption. So now it knows how to take clip embedding and map them to a prompt and from there the GPT knows how to generate a caption, because the mapping have learned to take the clip representation and embed it to a context that will allow GPT to generate something related. This is from ClipCap. You can check the paper for more details. Now, the fine-tuning phase of this mapping phase was actually a big issue, because what you can see is that once you fine-tune a network based on supervision data, you will end up with corrupting the data of clip, destroying the original knowledge, and limit the knowledge only to the data that exists in the supervised dataset. So here, COCO, which is the data that people usually use for image captioning, is only 118K images, and it's significantly lower than clip, so you can expect it to be the knowledge there should be much more limited than the one exists in clip. So when we use this approach that I showed before to generate a caption for the image of Cairo, we'll get something like a large building with a clock tower in the middle of a city, very generic, and we cannot see any clock tower here. And the reason it says clock tower is because COCO have many pictures with clock towers. So you can see it picked up biases in COCO, and it no longer has the knowledge that this is Cairo. Now I do want to emphasize that when you increase the data set, the size of it, and use the same approach, you'll get better results, because now if we use conceptual closed captions, you can see that it does describe the image as image of pyramids, which is much better. There is no clock tower, but again, it doesn't say it's Cairo. It still have a limited knowledge because it's not close to the amount of data they use to train clip. So we do get the idea that fine-tuning distorts the knowledge within the pre-trained clip representation. And now the question is, can we solve the task with no reliance on supervision at all? Because we see that learning this mapping based on supervision does limit the knowledge that the final method can use. And to do that, I wanted to think about the task as two separate tasks. Let's say we have one network that knows perfectly how to generate language, and it was trained to generate language that is coherent, human-like. This is the way humans talk, but it doesn't have real-world knowledge about images or a way to understand what is an image. The other task is comprehension. The other task is just understanding what we are seeing in the image and understand its relation to maybe different images and so on. So for language generation, we know that we have a language model that does that very well. Now, for comprehension, we have clip. If given text, an image of a Cairo, we have a score that will tell us this is Cairo. This is this text representation is very close to how the image is represented. They are the same thing. So we can get high score for an image of Cairo, maybe a good score for an image of a pyramid, and a very low score for an image of a clock because it doesn't even appear there. This is what clip gives us. So now let's see how we developed a method based on those insights. So a language model, it generates a word, the next token each time. It gives like a list of candidates. Here it tells that clock is the best next word. To complete the sentence, image of the city, the next word it predicts it's a clock. And pyramid is somewhere in the bottom. It still appears. It's plausible that it is one of the possible words that comes after city, but it's not very high. what we can do, okay, so we can calculate clip score for each continuation of the sentence. So now image of the city clock will get a score if we use clip of 0.1. And pyramid will get a score of 0.8. So we have probability for each one of the scores. Now, I also want you to note that the language model, the way to work, it has an embedded context. So what it means is that the history, the prompt that it uses to generate the next word is embedded in a way that they keep for each word the key and value of the transformer, the key and value representation. You can see if you look into transformer decoding why it's enough. It's mostly because they mask out the everything that comes after a word, and that the decoding only relies on the past. But please look at masked attention and decoding with transformer to understand why it's enough to keep those representations to allow transformer decoding. I do emphasize this because those representations are exactly what we are going to optimize. Let's see how. So first of all, we'll take the probabilities of clip. We'll call it P, and we'll create clip loss that asks the prediction of the language model, the logics that of the next word, to be very close to this probability with cross entropy. And we use it to build a loss and update the representation of the context. What it means is that we took with a gradient, we changed the representation of the context. We didn't change the language model, it's still frozen. And we asked the language model to generate another word, to generate the word again. Now you can see that after we did that, pyramid suddenly appears very high, and the language model also have in one of the high options the word Cairo, which is only based on real world knowledge. And we can run it again. Now we have a different P, and we create a loss with it. We update the representation and ask the language model to generate the next token again, and now we have Cairo and pyramid and as the next word. So this process of optimizing the next token is something that allows us to use clip to optimize for the optimization, but we never touched the representation at all, and it doesn't rely on any supervision. So you know that the generation will not be restricted by any limited data and will not include biases because of it. Now, another part of the optimization that we need to keep into account is that when we change something, we want to always be sure that we didn't completely ruin the downstream task. And here the downstream task is language generation in a way. So we don't want to ruin the way the language model generates language. We want it to be still a human-like language. So to keep the language correct in a way, we ask also that the prediction of the next token will always be close to the original prediction. So if you remember, the original prediction was like clock and pyramid was in the bottom and we couldn't even see Cairo. We always ask that the new prediction will be close to the original one, and we add it as another term. So the final token optimization here is considering both the visual reasoning and also the language element. So now back to our example, what happens when we use this approach. So with ZeroCap we get the caption, the Egyptian city of Cairo, which involves both real world knowledge. It can recognize that this is the city of Cairo, and it also very human-like sentence. So we got everything that we wanted, and I I'll be honest, when we just released this approach, I think it was very surprising to see, once you don't use supervised data, how much better the captions are. So with supervised methods that did captioning, you can see that all the captions are very so it's limited, and they look quite the same, and they are very kind of dull, like they are not very good captions. And what's surprising is that those clipvl and winvl are very different architecture. They even use different pre-trained representation. One is based on clip, the other one is based on another visual transformer network. And you can see that despite that, the captions are very similar. So let's say in the middle we have a TV room, so both of them say something like a living room with a television and a bookshelf. It's correct, but two methods are generating almost exactly the same caption, because this is the way the annotators, this is the type of language the annotators use in Coco. Now with our method that is, we didn't use any supervision, you can see that the caption is much more human-like, and the caption is a room dedicated to games and other forms of entertainment. And with our caption, we also have real-world knowledge. We do recognize this is the Toronto Blue Jays. And what's surprising is that we also noticed that our method could have in the caption can recognize text within the image. Like here we have Sean's truck, and the caption could recognize that the word Sean is written on the cake, which is very surprising given that it wasn't really trained for that. It just means that this kind of comprehension capabilities exist in clip. It means that images with text appears next to the embedding of the actual text. And with our method, we could reveal that. And the real-world knowledge that this method have is really vast. You can see here some examples. It can tell you about cartoons or movies or places. It recognized everything because it was trained on 400 million examples across the entire internet. And I think what emphasizes this capability the most is the vocabulary metric. It checks how much diverse the language the model use. By diverse, I mean that it used novel words and novel sentences. And you can see that the previous methods that use supervision are quite limited. The best one had something around 2,000 word vocabulary, while our method on the test, we have 8,000 word. That means that the captions that we generate over the tests are different from each other, are very unique, and this is something you want your method to have. Now, another capability that we found out while experiment with this approach is that clip, because it's a vector space, could allow us to merge concept or to do some arithmetic over images. What do I mean by that? Suppose I have two images and I want to describe both of them in some way that will relate to both of those concepts. We can take clip representation, embed each one of those images to a vector, and add them together and get a new vector. Now, the new vector, we can use it to generate a caption just like before. And what do we get? We get something very interesting. If we try to describe the word, the phone here, when we add a vector of an apple, we'll get a caption that tells Apple's iPhone. So it learned how to merge two concepts into one. If we have a tree and the flag of Canada, it generates a Toronto maple, which is a tree that comes from Canada. And this was very nice. We have now a way to describe two photos in a semantic manner. What happens when we subtract two images? So I think this was even more surprising, because subtraction in a vector space represents direction. And direction kind of gives you an attribute, because let's say we look on the first two images. We have an image of an airplane, a real image, and a caricature representation. The subtraction creates a direction from the airplane to the caricature, and we get the caption for this subtraction. The caption that was generated is a caricature illustration. It actually managed to describe the attribute that is the difference between those two. When we look at the image of many basketballs and the image of one basketball, the direction from one to many, the caption that we got is a bunch. And the same thing we can get from green apple to red apple. We got a caption with the word red. From red to green, we got a caption of the word green. So you can see that it does capture attributes. And taking those two ideas together, we got something very nice about analogies. We managed to solve analogy tests with images. And what do I mean? If I look, let's say, on a man and a king, this is a famous example from a paper about NLP, WorldNet, if you remember, if anyone aware of it. But let's see how it's done visually. If we take an image from a person to a king, we get and subtract them, we get the direction of royalty. Now, if we add this direction to an image of a girl, we'll actually get a young queen as a caption. The same thing can be done, let's say, from a chicken and egg. It represents a vector that tells something about production of food. When we add it to a cow, we get the caption a cow's milk. So it knows that milk is something that cows produce. And we realize then that this is actually a new way to extract knowledge visually, because now we can create a vector. Let's say we take the flag of the American flag and picture of Obama, and the subtraction give us direction the president of. We can add this vector to different flags to get the caption Angela Merkel for the country Germany, Cameroon for the country England, and Putin for the flag of Russia. That means that we could kind of ask the president of different country just based on visual analogies. And we can even do the same thing with the CEO of. We created a direction with different CEOs just to show you that this method is quite robust. And then we can tell that Zuckerberg is the CEO of Facebook, and so on. And this is the first time you could actually solve those analogies, those visual analogies with visual input and not text. And from here, we could ask question visually. We could ask the food is from which country by subtracting a pizza from Italy. When we add it to baguette, it generates France, and so on. I think what's really nice is because Clip is multimodal, we can do the same trick with text as well. Like, let's say we want to ask, give me the night equivalent of this image. So we can take image of a day, image of a night, subtract them, so it creates direction from day to night. When we add it to breakfast, it generates a caption dinner. So it tells us the night equivalent is dinner to breakfast. Or we can ask what is the capital of this country. We have image of Tokyo and flag of Japan. So instead of finding the image of Tokyo, we can just use the text to generate the representation. When we add it to French, we'll get pairs. So it's multimodal, and this is why we can solve those analogy in text. Now, I think when you start to solving those kind of problems, the first thing you can think of is, okay, we need a way to measure how good our method with those kind of relation thinking. And for that, we came up with a new evaluation for multimodal embedding. And this is, again, very similar to the way people measure how good text embedding is. And with zero-cap, because we actually can solve those analogies, and it allows us to tell how good, in a way, clip plus zero-cap in solving it. And we introduced this new benchmark to the world as the first approach that can solve it. So I don't have a lot of time to get into this work, but I'll just mention it briefly. Given the fact that clip represent attributes as direction, as we saw before, and in a way the representation is kind of compositional of different attributes, wanted to be able to find out what are the most significant attribute that representation use for an image. So for that, we came up with the approach that asks, given a set of images, the captioning model to generate the attributes themselves. And each time we want it to generate a new attribute that is orthogonal to the previous ones. And we also want this attribute to have high variance across the images. It means that it is significant attribute that changes a lot between the images. So here, giving a set of images, the attributes that were generated are car park. This is the most significant attribute. So it's quite nice to understand that the way they represent the image is either the car is driving or it's parking. The next attribute was, is it SUV or not? The next one was about the color, is it red or not? And the next one was about luxury, is it expensive car or not? And this is quite nice way for you to get the topics or concepts that the clip builds an image with. So you can get into the paper to get more information. Maybe you have ideas to build on top of it. It actually used blip and not clip, but I won't get into the exact details, but I think it's a very nice work, and you can use the results to other projects or ideas. Now, I want to extend the method that we did before to videos in some way, and why I can just use it to videos to begin with. So if you remember, in the previous method, we optimized each time a token while the language model was generating the caption. And with videos, it's quite challenging. Why? Because finding the next token to describe an entire video is quite hard, because in video there are multiple frames. Suppose we pick the 4 significant frames in a pre-processed step. Then we ask clip, find me a token that is close to all those 4 frames. It will be very hard to find one token that is relevant to all of them. In a way, we need something that will not optimize a token, but we want to optimize the entire sentence, because entire sentence can refer to different temporal events, and then it will make much more sense to optimize the entire sentence to align with a complete video. So now the question is how we take the previous method and change it to something that does not optimize a token each time, but an entire sentence. So for that, we change a bit the part that we optimize. Instead of optimizing the internal context of the language model, we start with pseudo tokens that will be constant for many sentences that will generate. So we start with randomly initialized pseudo tokens, and we start by describing the sentence, by describing this image with some randomly initialized tokens. We use some tricks to get some bootstrapping of the process that will be similar to the image, but as you can see, it's not very accurate. So it tells something about Egypt, but it's not Cairo, and it has a lot of mistakes in it. Now, what we will try to do is to optimize those pseudo tokens and generate another sentence. In that manner, we'll get a loss across the entire sentence, and each time we'll let the language model generate a complete sentence. We won't interfere the way it generates the tokens themselves, and with that, we'll get a method to optimize a full sentence. Now, just to make sense here, we are optimizing for images first, just to show you the differences from the previous method, but in a few slides I'll show you that it also works for a complete video. But let's see how it works for images first. So we take clip with the entire sentence and we optimize the pseudo tokens. Now we generate again, and we got now image showing Cairo, the capital city of modern civilization. This is the second generation. Now we repeat the process. We optimize the pseudo token and generate again. So we optimize the pseudo tokens with a loss. We generate again, and now it tells you image showing Cairo's ancient city and its many wonders. This is the best caption that you can get, in my opinion. It's very fluent, and it's also describing very well what we see in the image. And I will say that the way we measure this improvement is by measuring perplexity, how fluent the language is based on a different language model. And we saw a significant improvement with this approach. And honestly, it's mainly because we didn't intervene the token generation. Like we let the language model to generate the entire sentence without any intervention, without interfering it at all. And it did allow the language model to create the fluent language that it knows how to do, but now with the right context. And you can see many examples how good it is. So we have here an image of Bill Gates now with the token level optimization with zero cap. We got a genius CEO who is not genius in the world of Silicon Valley. So it's not very fluent. It describes something about Bill Gates, but because it optimizes a word each time, it looks very weird. And with our approach, you can see it generates Microsoft billionaire and philanthropist Bill Gates, who is the chairman of the foundation. And here we have to cut down the generation, but the image caption generation. But you can see it's very fluent and it's very accurate. And you can see other caption, the world's largest word in China, complete with a stunning view from above, or Beijing futuristic office building. Again, those are perfect captions. And I think the level wise optimization was much better way to create captions, the sentence level. And for videos, it also works quite well. So if we do the exact same approach again, the way we did it in details is creating a clip loss for each frame and adding them together. You can look at the paper for the exact details, but it's a naive extension. The main difference is optimizing the context pseudo tokens instead of optimizing for each token every time. This was the main difference. So when we use the method to describe a video, we get the first caption quite generic, a very bright flash of light that appears to be coming from the full moon, something that is generic. It's in terms of human-like, and it's very good sentence, but it doesn't describe the video very well. And as we continue to generate sentences, it starts to be more accurate and related to to the video. So now we have Naruto flying away in a flash as he appears with the full moon. It says Naruto, and I think this is something I really like about this method, because it's getting closer to describing the actual figure that we see here, which is Goku, by describing another entity that is close to Goku. And Naruto is also an anime character that looks like Goku, and he first mentioned Naruto. This is something that happens a lot in this method, like the early sentences are getting close to something that is related, but it's not exactly it. And you can see that after 20 sentences, we did get to Goku flying to space with a giant beam, which is, again, in my opinion, a perfect caption for a video. And what we did see with this method is that we improved all the metrics that related to video correspondence. Those are metrics that use retrieval, like when you generate a caption, you want it to be close to another video with a retrieval model. And I think the most significant thing, again, is the perplexity. Like the language that you generate is really human-like and fluent. So let's summarize those two methods. I want you to consider this abstract representation of how to solve problems. We have a generative model, it usually have a conditioning, and we have a discriminative model that is used for comprehension. This is the knowledge source. And both of those methods, we have a discriminative model that tells us something that the model generated is bad. It can tell if it's good or bad, and we can optimize the conditioning in a way that will take this into account. Now, the generative model can generate again, and the discriminative model can give another feedback. So now we can tell that it's better, but we can keep improve the conditioning and until we get a good output. So this kind of method is something that can be useful to many other tasks, and this is a very good way for us to take a knowledge and add it to a generative model. Now, I think the question that many of you may ask is, so now just to summarize what are the pros and cons of our approach. So our approach is zero-shot. It means that it doesn't need supervision, which is expensive, and also, as I said, distort the knowledge in the representation. We also do it during inference time. We don't require a fine-tuning step that usually takes a few hours or even days to learn mapping or something like that. And because of that, the method can be seen as a plug-and-play approach that you can easily take any different discriminative model, maybe new versions of Clip, or change the language model, and it's very easy to see how it affects the performance. Now, the cons are that it does take some time to generate, let's say, a caption with this method. It could take even a minute. Usually it's less. You can control how much time it takes, but still it takes some time. And the question is, can we avoid maybe the long inference time? So the answer here is that we can, but again, we need to train a mapper for it, something that will take the representation from a discriminative model and map it to the conditioning. This is the first approach that we saw, and then we lose all of the cons, all of the benefits that I talked about before. But still, I want to just emphasize that learn a mapping between discriminative representation to the conditioning. It's still very useful, and it's a very strong baseline. If you need somehow to take knowledge from Clip and integrate it into a generative model, learning a mapper it's a useful trick. And maybe you can come up with ideas that the mapper, for instance, will not rely on supervision. Maybe we can generate examples using the previous approach and train the mapper with it. I let you think about it. But for now, we need maybe a way to have a mapper that doesn't rely on doesn't rely on supervised data. Now, another point that I want to really emphasize is why we need to have why Clip only have given us a discriminative score, one that just tells us if an image and text are similar or not, and why they didn't give us a method that takes an image and generate text. What Clip wanted to give us is embedding that correctly represents image and can distinguish between different concepts with this representation. And they have shown that if you learn things discriminatively with contrastive loss, it's much more efficient. It means that those embeddings can be used to distinguish between concepts much better. They refer to it as a zero-shot ImageNet classification. You can get into the paper to understand exactly how they evaluate it. But you can see here the two methods that created the representation with the task of generating the caption or maybe predicting a bag of words of the text that correspond to the image, shown a much weaker performance than the method that was trained based on contrastive loss. So I think in general, it gives you something that teach you how to acquire new knowledge, and every time you have a new data set, it will probably be easier to learn discriminatively how to distinguish let's say images or different kind of text instead of trying to generate the data and maybe out of it get a representation. So in general, it's better to learn new knowledge discriminatively and kind of influence a generative model with this information. So overall, I tried to give you in this lecture that machine learning requires various cognitive skills. It requires attention that allows us to remove non-useful information. And I showed you many works that involve multimodal attention, a way to build architectures that take into account different modalities, more than two. And I think using those ideas, maybe people can come up with how to improve current architectures, especially if you see any pooling layer in modern architecture. You can change the pooling to attention layer, and if you want to work on something like that, let me know. I also said that another skill that is useful is perception. That means identify all the entities. And I showed you a very novel and useful technique that teach where to look. Now, again, if you have an idea how maybe to use different supervision or something along those lines to change the places that model looks, or to make sure that it looks on everything it should look, like maybe even creating a new metric, again, let me know. We can work on that as the project. Last but not least, I talked about the comprehension skill. That's more about recognize concepts and their relation. It tells you that any model that we have needs some kind of knowledge source, and usually it comes as the form of a representation or some form of a or model that was trained discriminatively, and we can use this knowledge to improve generative tasks. And I showed you a few tricks how. I showed you how to create image to and video to text, how to allow a generative language model to handle input of image and video based on clip. And also I showed you with just one slide, but it was still a nice idea that maybe we can extend about how to reveal in a multimodal representation the attributes that that are used to create a representation for an image. So everything we talked about up until now is about improving skills that people have worked on, and I want to show you that there is another skill that I think it's on early stages where people explore those abilities, but it's still not solved. So let's consider this question: how many stars are in the image? And for this question, the model still, even if we have perfect attention, perception, comprehension, it's still going to be a very challenging question. And most likely it will answer something like many, or it's not really solved by any of the previous skills, at least not naturally. And to solve it, there is another cognitive skill that we can look into, which is problem solving. This talks about the ability to create a set of strategies, such as computer modeling or simulation, to find solutions to problem in an orderly manner. And this is something that is still missing in most common networks. And I've seen some solution that attempted to solve it a few years ago, but I think nowadays we have tools that will actually allow us to solve it and to make an improvements based on this problem solving approach and how it's actually look like, what it means in deep learning. It means that when we have a question and an image, instead of instinctively, like we generate the answer, we will ask an intermediate step that will generate a code. Here we have a very complicated question: how many muffins can each kid have for it to be fair? The code that was generated took this question and generated something in Python that tells, first you need to find the muffins, then you need to find the kids, and then you can actually perform the logic that the question requires. It's counting the number of muffins, counting the number of kids, and returns the final answer. This is how problem solving can be done with modern neural networks, and this is the future we are probably going to see when we are talking about decision making or solving any task in deep learning. And I think it will be very nice if some of you can think about projects maybe in this direction. And I think in general, the new tool that gave us this solution is LLM. We have now large language models that can take us from the first and instincts of the system 1 kind of approach to the system 2. What is the system 2 approach? It's more about rational thinking. Like you need to think, does it make sense? And some of the works that already use this kind of system 2 thinking, there is a work that creates attention with LLMs. It asks the LLM, where should I look at? There is another work that given an image, it doesn't want a caption that describes it. It asks, does this image even make sense? So yeah, it can perceive Einstein, it can perceive the smartphone that he have, it can comprehend those two concepts. Now with language model, we can even tell those two concepts, they don't make sense because all the reasoning that we have that can be done based on with language model. Another interesting paper took a language model and added a step to an agent that traveled the world with the question, what should I do next? So it's kind of imitate the actions that reinforcement learning kind of trying to optimize what actions you want to do, and ask a language model to do it, to think about it rationally. So I think it just gives you some intuition to maybe how the future will look, and maybe we can come up with some interesting project based on large language models. So that's it. Now, if you have more questions, please send me an email, especially everyone in reserve duty, feel free to reach out. And any question about projects and so on, I'm here to help. So just send me an email, and thank you.